developing for the programming architecture. So the name of the software we're developing is it's a brain-style computing architecture BICA for short. And so Takahashi talked a bit about the central WBA hypothesis. In short, it means by combining machine learning modules, we can build up a brain. So we want to test this hypothesis. So we take the constructivist approach to this hypothesis. So we thought about some sub-hypotheses, modulatory of brain organs in machine learning, and emergence of cognitive functions. This is not the exhaustive list. There has to be some more hypotheses to test, but still we are studying with those this list of the hypotheses. The first one is modulatory of brain. So brain apparently is a set of anatomically independent organs. So if you look at this picture, there's a nerve cortex. And in addition to this, we know that there are some other organs like a basal ganglia, thalamus, hippocampus, and those structures are made by the development process of the brain. So probably this is okay. We could assume some modularity between those organs. If you look at the nerve cortex, most microneurons connect to each other by maybe 2 steps. The connection is very dense, but still we use the diffusion MRI. We extract some network structure. This is actually witchcraft connection. And if we use functional MRI, we see some localization in brain activities. There seems to be some modularities. We have to test this. And the second thing is the brain organs and machine learning. Brain modules must be computationally represented at the functional level, but not at the physical level for the programming architecture project to be successful. So that's what we mean is that we want to model that not by enumerating all neurons in synaptic connections, but we want to model those modules by defining its behavior with some very different computationally consistent algorithms. So, and in addition to that, all machine learning algorithms used in the WBA must be known by the completion of the project. The third thing is emergence of cognitive functions. So there seems to be some qualitative gap between functions of each machine learning modules that we have now and the cognitive functions that the entire brain exhibits. So there has to be some additivity. And so to do that, so we have to test this hypothesis. We test this hypothesis by combining machine learning modules to form what we call machine learning complexes, the structure that is consisting of the multiple machine learning modules. So this was actually, in some part, we discussed in last year's NIPS by the people in Google. So some good example is Baidu MQA, a multimodal question and answer system. This combines actually 4 machine learning modules, convolution network, and the 3 recurrent neural network, actually those are LSTM. And another good example might be Google's DeepQ network. This is a famous program by Google, DeepMind. Here the input is a visual, and the output is digital, the discrete, the command to the game controller. So this combines with the deep neural network and the paradigm of the reinforcement learning. So I think there are basically 2 options in doing this, reforming machine learning complex. One is composition, the other is hybrid. By composition, I mean connecting machine learning modules without modifying them to form a larger structure. And by hybrid, I mean combining more than one machine learning algorithms, not implementations, algorithms to come up with a more complicated algorithm. So some examples of composition is, as I said, MQA, NeuroTalk, and BRED. The hybrid Google or secure network is a good example of this type of structure. So for this, the software platform doesn't have a very important role, but for composition, the software has to support hierarchical model structure. And another thing important is distributed representation. Another design decision we make was this. The modularity of rank hypothesis eventually boils down to intermodular communications in the form of numeric vectors representing firing frequency of frequency. That was our design assumption we made. And on the other hand, in general, cognitive architectures often use symbolic representations. So our design of this software is like this. So inside the module of the brain organ itself, the communication has to be distributed. But inside each module, we could somehow use, if necessary, symbolic representations. So for that, BICA, our software defines three kinds of computation units: component for which doesn't have this distributed representation restriction. Module is does have the distributed representation restriction. So this is for the brain organs. This is for more finer grained computational units. So in this way, we identify some desirable features for the WBA software platform to be useful. We identified those 8. The software should be used to form some module library of machine learning modules, and it has to be able to hierarchically connect those modules. It has to define unified messaging protocols. It has to define unified sensor actuator interface to interact with the environments. It has to be real time. It has to be scalable. It has to support learning curricula, and it has to be community-based. So this is an example of like a component computation unit, basic computation unit. Each unit implements a single machine learning the implementation. There's an input ports, output ports, and the user defines a fire function, and it has an internal state. So this is the basic unit. So the fire function here is it takes the input information and the internal state and converts this into the output state and the internal state. It updates the internal state. So it also defines a larger scale of computation unit called module. The top level one is called agent, which is a module. This is a subclass of module. And it defines sensor interface, actuator interface. And the module can have can contain multiple computational components. And it can also have sub-modules. So it can represent the hierarchical structure of the computational structures. And concurrency is also important. So brain is said to exhibit a computational speed of about 1 to 10 petaflops. That means we have to combine hundreds of thousands of cores to make it possible. So this is a basic file function. And in the implementation, actually, this is not a computer science conference, and I'm not getting into any detail, but basically, we break down this procedure into 3 phases. And the main thing is here, the fire function. So this is a heavy computation. But we also define input and output procedures, which are likely. There are many possible optimizations to make the impact of those features actually. And I basically explained the execution layer of the whole entire BICA software. But in addition to this, there's a hardware layer. So it has actually 6 layers structure: hardware layer and execution layer. On top of that, we have a module library, and we define the BICA language to describe the connections between those modules. And we have the cognitive architecture, which is the application we want to run. And there's a user interface. The actuator sensor interface on this layer. So I'm going to show some examples. So first example, I show is based on the BICA implementation of the cognitive architecture called CHITA that Yamakawa-san and Hiroshi developed in the late 90s. This is short for the cognition-based architecture. It is kind of goal stack-based architecture. There is an environment, sensor input is given to here, and the actually the output. There's a goal stack, which is in the shell memory, and there are multiple modules, and there's a payload tree, because this is goal stack based. And this is an implementation tab. From the start point, the agent has to get to the goal. To do that, it needs to get a key. So initially, the behavior seems very random, but afterwards it gets more efficient because it learns the cognitive distances between the participants. The second example is we use the gazebo simulator. So we connected BICA and the gazebo. And we use the Totobot simulation simulated agent. So we set up the radio maze structure. And we define three components: sensor component, decision component, and motor component. This example is just a toy, so the motion is basically random, but we can do this. So basically, that's it. So this project is made possible by lots of supporters. The Durango, Toyota, Panasonic, basic company by Suma, and in addition to those other supporters. So in this afternoon, we have a workshop from till 5:40, and we're going to discuss some more details about our project. So we will any of you to come to the workshop and discuss. Thank you very much.
Questions? Already know.
I don't need a mic. You haven't mentioned natural language processing or understanding in your talk. I'm sure it happens, but maybe just a few words about it.
You want to say something?
Of course, our mission is to create a human-like artificial intelligence, so it is necessary. But we starting based on the brain. So now, of course, you know the neuroscience. Neuroscience technology is very rich in the mouse or that kind of rodents. So we go step by step. First 5 years making this platform and architecture and the kind of things for rodents. And second step is monkey or something, that kind of thing. And last step is the human. So now we started last year, so just rodents. So we don't have so many ideas about the language. But some people with somebody of course interested in the kind of area. So main step is the rodent, but they are parallelly studying.
I have a second question. You have available the source code or the code of your system, we can get access to it by internet or something?
I was going to mention this, but I skipped because of the time restrictions. So we're going to discuss in the afternoon session. So we are completely open. That's our principle, our policy to make everything open, because we believe that the first AGI we develop has to be open, not proprietary. So source code is open. It's on GitHub. So I'm going to give the URL and then have conversation.
Other questions?
Will you use ROS or YARP or some kind of established framework?
So we have an interface to ROS. inside of the cognitive architecture, we compare the pros and cons of using the established software robot middleware, and we decided to create our own execution machine because the ROS is basically distributed computation-based architecture in which the latency of the communication between modules is up to some millisecond. So there's a the mechanism for inter-process communication is lost, but its use is complicated. So we decided to make our own to optimize for our use. But it is of course possible to use ROS to interface with robots.
I think that scalability much by the functional programming method.
Yeah. The functional programming is, I think, an interesting paradigm to use for this. But do you know some examples of, for example, using functional programming for implementing deep learning artificial neural networks? If that's possible, then
basically functional programming. It's very close. There are no just there are papers on that. There are no functional programming. Very closely related.
So yeah, in our BICA we use Java and Python and C++, which are not completely functional, but basically as I explained, the file function that we define is designed so that it ensures concurrency. This is basically functional, so I think it's possible to use the functional program. So as for performance, I didn't show this, but I created some requirements. The final frequency of neurons is about this. So the time scale is 1 millisecond. So the overhead of communication in this platform has to be negligible compared to this. So it's 10 microseconds something. And in our prototype, the latency is about 100 nanoseconds. So it meets this requirement. As for scalability, as I said, human brain is said to be about 1 petaflops. That means hundreds of thousands of processes. So that's the reason here, making emphasis on parallel computing.
Okay, then there is one final announcement over here.